So, last class we learned about end behavior, given a polynomial's degree and its leading coefficient, and how we can use those patterns to help predict what those graphs look like. And then we just finished watching videos about evaluating polynomials using direct substitution and synthetic substitution, which also gives us more insight as to what's going on these functions when we graph them. And now I'm going to give you another tool you can use, which is the fundamental theorem of algebra. And this is a really fancy name for a pretty basic concept, okay? So the fundamental theorem of algebra says that an nth degree polynomial has exactly n solutions, okay? So I know this is like fancy math talk. So let's look at some concrete examples. So our first polynomial, this is a quartic polynomial because the highest power is 4. And we know because of the fundamental theorem of algebra that says an nth degree polynomial function has exactly n solutions, that this has 4 solutions. So I abbreviated solutions here to take up less space. I ran out of room. Okay, so let's think back to last class when we first started talking about quartic polynomials, and I drew you guys a little function that looked like this. It was like a lopsided W, okay? This is what quartic polynomials sometimes look like, but remember I also gave you another example of our most basic quartic polynomial, the parent function, which looked sort of like a flattened out quadratic. No sharp turns, but nevertheless looks more like a quadratic because it's just your basic parent function. Okay. So this has 4 solutions, and I want to just clarify, though, that they don't necessarily have to be real solutions. It could be 4 imaginary solutions, or it could be 4 real solutions. So we'll get more into detail about that later, but I just want to clarify, they may not all be real solutions, but it does have 4 total between the real and the imaginary solutions. Again, we'll get more into that later. Okay, so the fundamental theorem of algebra, another part of this is how many turning points we have. So I wanted to look at both of these concrete examples that you've already seen and check out how many turning points we have. We have 1, 2, 3 on this kind of more complex looking quartic polynomial, and then we just have 1 here, okay? So I want to clarify again, you can have up to 3 turning points, okay? Does it necessarily have 3 turning points? Well, we see with this example that it doesn't always have to have 3 turning points. But what is nice to know is that you can have up to 3 turning points. Okay, so let's look at another example. And again, this is an example that we looked at. You've seen cubic polynomials, so we know that this is a cubic polynomial because its degree is 3. Okay, so this has up to, it has 3 solutions total. However, those solutions may be comprised of real and imaginary solutions. So it has 3 total, but some of them may be real. You could have all 3 be real, or some of them may be imaginary. Again, we'll get more into this later. Okay, now let's use what we already know about cubic polynomials just to visualize this. So we talked about how they have this kind of S shape, and here's a more complex looking cubic polynomial that's a little bit curvier than what I showed you guys in that first video on it. But how many turning points do we have here? So we've got 2 turning points here. Does it necessarily have 2 turning points? No, but it can have up to 2 turning points. Okay, so the big takeaway point of the fundamental theorem of algebra is just this. The degree, the highest power, tells you how many solutions you have, whether they are real or imaginary. We'll get more into that later, but that's the total number of solutions, okay? Then if you take a number 1 less, so notice we had 4 solutions here, and we have up to 3 turning points. That's 1 less. On this cubic polynomial, we had 3 solutions and up to 2 turning points. That's 1 less. Okay, so your degree is your total number of solutions, real and imaginary, and your number of turning points at most is 1 less than the degree. So you may want to jot this down in your notes just to reiterate this for you. Fundamental theorem of algebra, fancy name for a basic concept, says that your degree, your highest power, is your total number of solutions, and your max number of turning points, you don't necessarily have that many, but you can have that many at the most, is 1 less than the degree or your total number of solutions. And that's it. So we'll use this idea besides the idea of evaluating and end behavior and multiplicity of zeros. We learned that too. We can use all of this together to better graph polynomials. So I wanted to give you guys a concrete example of the zeros being real or imaginary. So we talked before, a quartic polynomial, that is something where the highest power is 4, the degree is 4. So we know because of the fundamental theorem of algebra that this has 4 total solutions. But remember I said that's 4 total. You could have 4 real solutions, okay? So let's say here's my x-axis, and I have crossed the x-axis 1, 2, 3, 4 times. There's 4 real solutions, okay? I could have 2 real solutions, okay? If I only cross the x-axis 2 times. It crosses here and it crosses here, but notice I didn't achieve that 4 total, so that means that I must have those 2 real. How many more do I need to get to 4? 2 more. So that means even though you can't see them, I've got 4 imaginary solutions as well. Okay, and how about this? If our x-axis is below the graph, and it never crosses the x-axis, but you should have 4 total zeros or solutions, then you know that you have all 4. You can't see them, but you know that you have 4 total imaginary solutions. So we have one more concept to talk about today, and that is the concept of conjugates. And I know we've used that word before, conjugate, which is where we used it before when we would rationalize fractions when we had to multiply by the conjugate, which was where we would have the same 2 terms, but we would change the middle sign. Okay, so there are 2 different kinds of conjugates. So one of these is a complex conjugate, and you've seen both of these before, but a complex conjugate uses an imaginary part and a real part, so we have a plus bi, and the conjugate of that would just be to have the a and the bi, but you switch that sign in the middle. So you've used this concept before of conjugates. Okay, so this is called a complex conjugate. Okay, and irrational conjugates, those have irrational terms in them. So we have the rational part, just the plain whole number part, and then an ugly square root. So for example, this could be like the square root of 2, something that doesn't simplify nicely. We call it irrational because it is a decimal that goes on forever. We can't write it as a terminating decimal. And that's something that you guys learned back in Algebra 1 about the different groups that numbers belong in. Okay, so we've got our complex conjugates and we've got our irrational conjugates. And this complex conjugate theorem says that if you've got one of these as a 0, the other one is a 0 too. And the reason this is true is because we've got our quadratic formula. And I know you guys know the quadratic formula, so I wanted you to write it out. But then think about why these theorems are true. So let's say you solve something by quadratic formula and your final answer that you get is 5 plus or minus the square root of 2. Okay, and some of you guys even go the extra mile and you rewrite this as 2 separate solutions for me, which will lend itself to you better understanding this here. You've got your 2 solutions here. One of them is 5 plus the square root of 2, and one of them is 5 minus the square root of 2. So you've got both of these together, and notice these are conjugates. These are irrational conjugates. So we got one solution here, one solution here. Let's say you got the square root, you ended up with your discriminant being -9. And let's say your final answer was 5 plus or minus 3i. 5 plus or minus 3i. Notice again, you've got those 2 solutions. You've got 5 plus 3i and you've got 5 minus 3i. So there's your complex conjugates. So this is why this is true. When we use quadratic formula, or anytime we've got a square root, you get the plus or minus part there. You have a plus or minus a square root, or plus or minus an imaginary number. So as long as you see a square root, or you see an I, you know that that needs to have a partner to it, because that came from using square root method or using quadratic formula, and every time we would solve things using a square root, we'd have to put a plus or minus in front of it. So what I want you to understand here is that these come in pairs. Okay, so if I give you 1, 0, say for example, the negative square root of 5, you should know, because that came from either quadratic, probably, well, you could get it from quadratic formula or you could get it from square root method. You know that when you solved, at some point you had x squared equals 5, and when you square rooted, or negative x squared, when you square rooted, you got negative, or, well, no, sorry, I didn't need that negative there. I don't know what I was doing. You got x equals plus or minus the square root of 5, because when you draw that square root, you also have to draw that plus or minus. Okay, so here's another example. So if, just to finish up that question, you've got negative square root of 5, its partner, I call it its partner, is the positive version of it. We know that they always come in these plus or minus pairs. Okay, so let's say you have a 0 of 6 minus 2i. Its partner, the complex conjugate, would be 6 plus 2i. Notice I didn't change the sign on the 6. I don't change these terms. I just changed the sign in the middle. Okay? So let's say you had a 0 of 3 minus 2 square root of 7. See if you can pause the video and come up with, hopefully based on these patterns you can, its partner. Okay, so 3 minus 2 square root of 7, its partner is 3 plus 2 square root of 7. And 3i, its partner, is negative 3i. That's because this came from x squared equals negative 9. When you square rooted both sides, you understood that you also needed to draw that plus or minus, okay? So this is where this comes from. It's kind of the working backwards from what you guys have already learned about solving either with quadratic formula or solving by square root method. Okay, and then the last section here in the notes, I think you guys can do this on your own. So pause the video. I'll give you the answers just to make sure we're all on the same page. But see if you just remember these things about the relationship between factors and zeros. All right, so our first example, we start off pretty basic. Switch the signs. You get 5 and 2. So positive 5, positive 2. Okay, our next example, x plus 6 squared. You only get one solution, and it's negative 6. But remember, we've learned about multiplicity before, so because of this squared here, keep in mind, I didn't ask you to do this, but I'd like you to be thinking about this. The multiplicity of this is 2. That means that if you were graphing this, it's going to be bouncing off the x-axis there because of that multiplicity. All right, the next one, again, I'm keeping you on your toes. 3x, think about it. If you set that equal to 0 and you divide by 3, you get 0. You do not get negative 3, you do not get 3, you just get 0. The 3 didn't really affect it, so it would have been the same thing had we had just an x out in front. X minus 2, there's an easy one like above, it's just 2. Okay, our next example, 4x cubed. This, just like the last one, it gives us an x-intercept of 0. Okay, so there's one of my zeros. And keep in mind, because of this cubed, this actually has a multiplicity of 3, which means it's going to cross and hug the x-axis. Okay, and then keeping you on your toes, if you want to, you could write this out, 2x minus 1 equals 0, and go through the motions of getting x alone. I know sometimes we get mixed up and we accidentally put the wrong number on top or on bottom, but you should get x equals 1/2 when you solve for x here. Okay, and then the last example is similar to that one. Again, if you need to rewrite it and go through the motions of moving it, go ahead and do that. Don't get ahead of yourself. So the answers you should have gotten are 1/3 and negative 5/6. Okay, so we've learned a lot of new things today. We've learned about these imaginary and irrational solutions that come in pairs, and this is going to play a big part in us putting all this together later on to graph these polynomials. We're going to use end behavior, we're going to use synthetic substitution, and so that we can evaluate and direct substitution. We'll use this new concept of the fundamental theorem of algebra, And we'll kind of put all these ideas that we've learned together, as well as multiplicity, which we just kind of got to review a little bit here, so that we can graph these and have a pretty good sketch of these polynomials without even using the calculator. So I hope you enjoyed this. You're all done with this section of the notes. So great job. Thank you for watching.